Welcome to Computer Networks. This is lecture 16. Homework 8 and 9 are out. We're just talking about homework 9. So let me just tell you what it's about. Homework 9 is about capturing packets on the air and analyzing it. Even though my laptop is sending a packet to one of the base stations here, everyone can hear it to some extent, right? So we're going to leverage that property of physical media to capture some packets and analyze things such as what kind of packets are being sent by who. And if it is an HTTP traffic, you can tell what kind of sites other people might be browsing. Right? And interesting thing here is when I was an undergrad, this was in very early 2000, wireless networks were relatively new, and one of the things that the TA did during the lecture is capture all the packets, and at the end of the lecture, he presented an analysis of what all the students were doing, which was not listening to the lecture. Because you could capture, the sites that the students are visiting, what they're buying, what emails they are reading, even, right? Because back in the days, most of the HTTP traffic was not encrypted. So you could actually learn a lot more. These days, it's a little bit harder. So what I've asked you to do in homework 9 is capture some packets and do some analysis. For example, how large are the packets? How many packets did you manage to capture in a certain period of time? And which sites were the most popular? I think that's one of the questions. And I've also asked you to do the same analysis on a standard trace that I provided. It has about, I believe, 30,000 packets. And the reason I said it might involve a little bit of programming if you want to is for, I think, one or two of those questions that I asked, it's going to take a little bit of time if you want to check all this manually. But if you write a little script to analyze this trace, and you just run that script on the standard trace, you have an answer, and you run that script on the captured trace, and you have that answer. You might have to go to the TA office hours to borrow a laptop to do packet capture if the software does not work on your laptop. I don't think it'll work on a Windows laptop. If you have a dual boot system and if you're running Ubuntu, it'll work fine. I think you have an option of running live Ubuntu without having to install it on your laptop. Just boot off of a USB stick and run the software. You could do it that way. If you don't want to go through that hassle, please go to the TA office hours. It just takes 5 minutes. All right, so that's homework 9. Homework 8 is about doing routing. Right? So who started looking at homework 8? Okay. All right, there's 3 of you. Good. Anything that you want to share about homework 7 to those of us who haven't finished homework 7? No? Was it straightforward? Was it what is tricky or confusing or took a long time to debug? I think those would be nice to share.
It was fairly straightforward. You have to remember to include the pthread library when you compile.
Okay, so you have to include the pthread library when you compile. Good. What else? How do you include pthread library when you compile?
So it'd be like gcc-l pthread.
Okay, so gcc-l pthread. So don't forget to put that flag when you compile. What else was confusing, time-consuming? This just to help each other.
I don't know if it was time-consuming, but getting the packet into a format that can be transferred across the network easily.
Mm-hmm.
I ended up just serializing it into a string, and then I serialized it when I sent it out, and then unserialized it whenever I got there.
I see. So getting data that you want to send in the form of a packet that you could send across the network was a little bit tricky.
Because you can't just send a struct.
Yeah, that's what I did.
How did you just send the struct?
You just give it the pointer to the struct and the size of the struct. But then on the other side, you have to be sure that your receive is also, when you say, store it here, you're giving it that struct and the size of the struct. And that worked for me.
Yeah. So I guess there were 2 approaches that we just mentioned here. One is serializing the struct before you send it, before you call send. Another approach is to just send the struct. How about host architectures? Do you have to worry about that?
Well, since we're all running it on the same, all the nodes are going to run on the same
Yeah.
host.
So even though you send binary structures, we're all running in the same
Yeah.
architecture, so we don't have to worry about that. Okay. What else? So you could
Yeah.
do what you suggested. That'd be fine as
I
well.
added a field to packet to
Hmm.
track who the previous hop was because
Okay.
I couldn't think of any other way to get that.
Okay, so someone added a field on the packet to keep track of the previous hop. Basically, if I understand correctly, when you forward the packet, you set the previous hop to yourself.
Yeah.
Why not look at the log files to see what the previous hop was?
Well, but one of the things you're supposed to log is when you log that you received a message.
Yeah.
You're supposed to log who the previous hop was.
Yeah, exactly. So the packet structure that I gave you is not necessarily complete, and you might actually have to add a few things when you go to homework 8. Okay, anything else that you want to share about homework 7? Okay. I almost forgot to talk about homework deadlines. I'm glad I have this slide here to remind myself. We decided to give you an option to use Thursday deadlines or Wednesday deadlines. This is a one-time switch. You can't just switch back and forth to get an extension. This is not an extension.
This
Okay.
will carry on through the rest of the semester.
Yes, this will be effective for the rest of the semester.
How is it not an
Downside.
extension?
It is not an extension in the sense that once you get into the habit of Thursday deadlines, then you have to do something every week.
But I guess I'm not seeing the disadvantage to choosing
Thursday.
to have it do
Yeah.
Thursday instead of Wednesday.
Oh, so if you have a lot of other homework that's due on Thursday or something like that, and if you are most effective doing homework towards the deadline, then maybe you want to pick Wednesday if your Thursday is busy. We received, I believe, about 15 emails. Did everyone send an email? At least those of you who wanted to opt for Thursday.
Yeah.
Okay,
Not yet.
not yet. Okay, do you want to?
Yeah.
Okay, all right.
So,
So you don't have homework that requires a lot of time that's due on Thursday? No one does?
No.
Okay.
All of my classes are Monday, Wednesday classes.
Okay. Even the homeworks are on Wednesday.
Yeah. Well, most of my classes require turn-in class, and then it's this class, and I have one other class, and that class is usually due on Fridays.
Okay. Yeah. So, anyways, if Thursday nights work better for you, please use that deadline. And if your deadline is Thursday night, then you have until Saturday night to turn in your homework. All right. In homework 8, you'll have to discover a count to infinity problem, come up with a topology that demonstrates this problem, and implement split horizon. Maybe I can show a demo of this next lecture on Monday. Today we're going to continue our discussion on BGP. Before we get into new topics, let's just do a very brief recap, really quick one. So this is a topology that we looked at last time. We have autonomous system 1 that has its clients with certain IP addresses, right? 1.2.0.0/16. You advertise your IP addresses or the IP addresses in your network to your peers or providers or even customers, right? You propagate that across the network, and you're changing this message when you're propagating this across the network. What is that change? It's a path vector routing protocol.
You have to include yourself.
Yeah, you have to include yourself. Let's look at the message that was transmitted by the router at autonomous system 2. The path is 2.1. That is what it says. Right? To get to those IP addresses, that's the path that's available through that autonomous system. These packets go to yet another set of routers, and depending on their policies, they pick the route that they want for that particular destination. Here's another example. Let's imagine B has these IP addresses a.b.0.5, a.b.0.6. So B is going to advertise, okay, I have a.b.0.0/24 to A. And A has not only B, but let's say many other customers. So it's going to aggregate these addresses and advertise a single prefix that's more general. We're talking about /23, right? To the other set of ISPs. Why do you want to aggregate? For example, B had the option of saying, I have IP address a.b.0.5, a.b.0.6. It could just advertise that to the rest of the internet, and the rest of the internet would know exactly where those IP addresses are so that we could send the packet there, right? Why aggregate?
It's less overhead, less stuff to keep track of.
Right. So it's less overhead. Let's think about overhead. So first of all, let's look at the number of messages. If B hadn't done the aggregation, how many messages would we have sent? 2, right? We had to say, okay, we have a.b.0.5, and then we'd send another message saying a.b.0.6. Instead of sending 2 messages, we can now just send one, a.b.0.0/24. So we saved on the number of messages that are being sent. A lot of times, we can announce multiple prefixes in the same packet. A packet could have a number of prefixes. But even then, we would, if we have a large number of prefixes to advertise, if you can aggregate that, we would still be sending fewer packets. Does that make sense? Okay, good. So what's the other type of overhead that we're talking about?
Your router has to keep a list of all the things it knows how to find.
Right, so let's think about router A. Right? Well, if there's any packet with destination a.b.0.5, a.b.0.6, A has to be able to forward those packets, and it has to know on which link to transmit that packet. There's 3 different links, right? One way to keep this information is by having these 2 entries in the table. a.b.0.5, send it along that particular link to B. a.b.0.6, and those packets along that link. So that's one way. But that is going to cost 2 entries. We could aggregate that and say if there's any packet for a.b.0.0/24, we're going to send it along that link. So we just used 1 entry. Any question about aggregation? So those are the 2 types of overheads. Yeah.
How is the AB05 and 6 related to the 0024?
Okay, so
Why
we'll.
24? Why 0?
I think we will talk about this way of representing IP addresses probably in the next lecture. But what that /24 means is it basically tells you what is the network address in a way. So I'm not showing you all the IP addresses that B has. B has many more IP addresses, and they all share a certain prefix.
Okay.
So if you think of these IP addresses as a sequence of bits, first 24 bits are the same. That's what we're saying. That's true, right? If you look at a.b.0.5, a.b.0.6, certain number of bits in the front, they're the same. They're the same. So when we aggregate, what we're saying is, if the first 24 bits of the IP address is this, then send all those packets down that link.
That's why A has a 23, because it gets AB0 and AB1, so it's only got 23 bits that are the same.
Exactly. So it has. So as you generalize it, you have fewer and fewer bits that are the same. That are in your network. So one other artifact of this way of aggregating the addresses is in the way we look up the next hops. So a lot of times we are advertising these prefixes. So some of the prefixes are going to be more specific than others. For example, let's look at that table on the top right corner of the screen. So there are 2 entries in that table. a.b.0.0 a.b.0/23 and a.b.1/24. Yeah. So which one is more specific?
The second one.
Second one is more specific. Does the first one include the second one?
Yeah.
It does, right? So let's say we receive an IP address a.b.1.0, let's say. And that router needs to decide where to send that. Actually, both the entries match, right? Do people understand that? A.b.1.0, they actually match both the entries, but we send the packet along the link that has the most specific match, also called longest prefix match. So that's the consequence of doing this aggregation. And just to recap, why do we want to do aggregation again? To minimize the overhead in communication as well as storage. All right, moving on. BZB provides a way for us to configure the router so that we can enforce any business relations we might have. BZB protocol itself does not propagate these policies. It allows us to select the path that would meet our business goals and propagate the paths or advertise the paths that would meet our business goals. Something that we talked about last time. Determined by path selection and advertisement, right? We talked about different types of relationships between different networks. We talked about customer and provider relationships. Usually customer pays the providers. So here's one argument. I go to AT&T and tell them that I'm going to give them access to, I have 25 nodes at my home. I'm going to give them access. I'm going to give them the ability to send packets to these nodes. I'm going to give them access to my network. And what will AT&T say? Because the nodes at my home, they're also part of the internet, right? They're part of the internet. Because you can send packets to them, they can send packets elsewhere. They're also part of the internet. So why does that argument not work?
Because AT&T has a lot more than 25, and they're not really gaining anything from adding your 25 to what they have.
AT&T is gaining something by being able to connect to your network at home, right?
Yeah. But proportional to what you're gaining, they're not.
Exactly. So you always need to think about who gains what and how much from these relationships. There's another type of relationship called peering relationships. If two ISPs, they decide to connect to each other without one party paying the other, those are called peering relationships. And usually these relationships exist across ISPs that are somewhat equal, or when both of them stand to benefit, to approximately the same extent. Right? One of the examples that we talked about last time was, let's say we have two different ISPs in the same city, in a given city. It just makes sense for them to peer with each other if there's a lot of traffic between the city, between each other's customers. All right? And this notion of lower tier ISPs. So the ISPs that have global reach, they're usually called tier one ISPs. It's like our tier one university. Then there are tier I+1 ISPs. These are customers of these larger ISPs. And the question is, how do these smaller ISPs forward packets to the destinations that they don't know much about? Right? This is by this notion of default route. And default route is something that we use even when we configure our laptops and other devices. Usually when you configure your laptop, you need to specify the default IP address, right? So if you don't know how to route a packet, then that's the default route to which you should send your packet so that it gets to the destination. Same with smaller ISPs. Smaller ISPs, they have a lot of customers, right? These are ISPs after all. If it is one customer sending packet to another customer, they can actually send these packets within their network. But if you're sending packets to some faraway customer that uses a completely different ISP, you don't have direct connection to those ISPs, right? For example, a small ISP, let's say in Houston, and you need to send an email to someone in a faraway country. This ISP does not have connection there. How do you send packets there? Because our small ISP is going to say, well, I'm not directly connected to that customer, so I'm just going to send it to my tier I-1 ISP. And then hopefully that ISP has a global reach, and you can send the packet to the destination. And this could happen at multiple levels. And we talked about this incident in Egypt, where someone was tracking the number of prefixes that were advertised, and at some point, some of these prefixes were not advertised anymore. So why is that a problem? So the network does not have to be physically disconnected, right? Because let's say you wanted to send a message to someone in some country, and routers in that country are no longer advertising the IP addresses that are in that country. Then the routers here, they don't know how to send that packet. The internet is not physically disconnected in this particular scenario. You don't necessarily need to cut the cable. Any question about that? Good. So let's talk about some of the challenges in BGP. It seems like it's an old topic, which it is, but still there are new problems being discovered, new solutions being devised, and let's look at some of them. First of all, convergence. Do we want the routes to be stable across the internet? That's the first question. All right. If we think about TCP, what determines the rate that you achieve? RTT certainly has a role to play, doesn't it? So what happens if the routes in the internet, they're changing wildly? The RTT might change time to time, right? That's not very good. So even from transport perspective, application perspective, this kind of large fluctuation in RTT is not good. Now, if you think about from just BGP perspective, let's say we're only concerned with the efficiency at which we can compute the routes across the internet. Is large oscillation good or bad? Is that desirable?
No.
Well, why is it not desirable?
Because you have to repropagate all that information across to find out the fastest route. So if it's changing all the time, you could be going across a route that's suddenly slow, but then that information won't get back to you for a long time. Depending on how quickly things propagate.
So you want routes to converge as quickly as possible. Why might routes change in the internet? What are some of the reasons?
Link goes up, link goes down.
Exactly. Link goes up, link goes down would be the most common reason, hopefully. Sometimes there are some configuration errors and so forth that also cause changes in the routes on the internet. Sometimes the policies might change. For example, this ISP is going to start charging you a lot more for the packets. Then you want to make sure these policies are implemented and are in effect as quickly as possible, right? let's go back to distance vector routing protocol. How quickly do those protocols converge? Is it instantaneous? It's not. And what is it usually determined by? How quickly they converge?
The diameter of the network.
The diameter of the network certainly plays a role. What else? I'll give you a hint. Let's say I'm sending updates every 5 hours. What's the best case scenario for discovering something new, good or bad, in the topology?
Well, the best case is pretty good. The best case is it happens right before your next update.
Yeah. What's the worst case?
Happens right after your update.
Yeah. In which case, it'll take at least 5 hours. Right. Now, what's the average case?
2.5 hours.
Maybe 2.5 hours, assuming certain type of distribution for these events. In that case, do you think if we make these updates go out more frequently, does that help with convergence? Yeah, it does. Okay. How frequently should these updates be sent in that case?
As frequently as you can without drowning yourself in updates.
Yeah, so there's a limit, right? So that's actually a real challenge. So it's not just without drowning yourself. There is another thing that you might want to think about when you try to determine what is the best update frequency, which is also the nature of failures or discoveries that you anticipate in the network. Right? It also depends on that. So let's think about how routes might change when we have an outage in the internet. So these are autonomous systems, and the paths are indicated in the diagram. For example, the path to 0 from 3 right now is 310. From 1 it's 10. From 2 it's 20. Let's say that link breaks 10. What happens in that case? Well, one is going to find out that the link broke. How will one find out that the link broke? So you're going to go through some of these discoveries yourself when you do the next homework, because you're building a real routing protocol. So can you guess how one might find out that the link broke?
Stops getting traffic from 0.
Yeah, you might stop getting updates from 0. So let's say we have a system in which everyone is sending update, let's say, every minute. And if you don't receive any update for a minute or two, or let's say 2 minutes, then you know that there might be something wrong with either the node or the link, right? So what does one do once it discovers that the link is broken? Well, it has to find an alternate route. Right? It might say, okay, let me use 120. How does it know to use 120? Well, it has a list of all these possible routes, and it was just selecting the best one from the perspective of its policy earlier, right? But now that route is no longer available, so let me start using 120. And 1 is going to advertise that route, 120 to 3. And 3 is going to say, well, the path from 1 is no longer 10, it's 120, so I'm going to actually switch to this other route, because that's better. All right, so this is how the changes are propagated. You could think of a similar scenario when you discover a new path. The nodes go through a similar decision process. There is one thing I would like you to note, which is when the nodes try to find the next best route according to their policy, they're exploring different paths, aren't they? You have a list of possible paths, and let's explore them. That's what the nodes are doing, right? And turns out this exploration can take a long time in certain type of topologies, when certain types of links break. For example, let's say we have a destination 0 and we have nodes 1, 2, and 3. So, all the nodes, they prefer the route 1, 0, right? 1, 0, 2, 0, 3, 0. So that's the most preferred route. But that's not the only path that they have, right? They have other paths too. For example, node 1 also has a possible path 1, 2, 0, 1, 3, 0, and the other nodes have similar paths as well. If you look at node 2, it also has 2, 1, 3, 0, for example. Right? So these are all the possible paths that they have, but they prefer the shortest path for now. Let's in the beginning, the destination 0 exists, and all the nodes are using the direct path. What happens when the destination dies? First of all, how do the nodes know that the destination is dead? It's the same idea of keep alive. So that idea is called keep alive, which is you tell someone that you're alive. You tell someone that you're alive periodically. And when someone does not receive a message that you're alive, then it's a reasonable assumption that you're dead, right? So what happens when the destination dies? What is one going to think?
They're going to think that's their link to 0 instead.
Yeah, so the nodes are going to think that the direct link is down. That's what they're going to think. And what will they do? They will withdraw the direct route because they're advertising this direct route to other nodes, right? Those links are gone. Let's think about autonomous system 2. So it's going to say, okay, well, 2, 0 is down. So let's try 2, 1, 0. And it turns out 2, 1, 0 doesn't work either. Let's try 2, 3, 0. Turns out 2, 3, 0 doesn't work either. So let's try 2, 1, 3, 0. And okay, well, there are no more paths. So this convergence could be slow because you don't go through these steps just within one node, right? Because you guess that 2, 1, 0 might still be good. And you ask the router, okay, is that still good? Using BGP protocol, of course. So you need to go through a series of announcements and withdrawals, and finally you converge to the state in which every router knows that there is actually no way to get to 0. This convergence could be slow because you're exploring all the possible paths in the network. So that's one potential challenge in BGP. Whenever there are changes in the network, thinking about, okay, are we going to converge quickly? Because the quicker we converge to a stable solution that's correct, the better it is for us because we know exactly what happened and maybe we can direct resources to fix that problem, right? Okay. All right, let's take a very quick break and then we're going to talk about some unstable configurations. You can stand up if you want.
Just me.
Yeah.
Getting the existing methods of DLL. Or the existing process. I'm sure his latest review was it's like, why do you need this class that's central? And there's all the actual work. And then he says, okay, you need to about doing this. I'm like, that's what the piece that does that.
What are you guys talking about?
Software design.
Oh. So it seems like a lot of you are taking software design, some of you are taking operating system.
Both.
Both, okay. Software design is probably the most work, isn't it?
I don't know. This one's pretty close.
This one is pretty close, okay.
Yeah, I think it's.
With software design, the amount of work depends on how good you are at deciphering his feedback.
Okay.
Because he lives in Colorado, and so all the lectures are by video,
Uh-huh.
and for all of the assignments, it's all done on his SVM.
Mhm.
And once a day, you can ask him to review what you've got, and he'll tell you, you're making progress on this, you're doing this right, but you need to work on that, and so on. And so the better you are at deciphering his feedback, the faster you'll get to the correct solution, and the less time you have to put it.
Ask him about our homework one, or assignment one. He's like, you can make this better. I'm like, how? Because he told us that 3 or 4 times. We're like, all right, let's try this, and then I looked at his answer, and he said, do these 2 things.
Yeah.
It's like, we had both of those at one point. You kept telling us to redo it.
Yeah.
You didn't tell us this was good. You just told us to redo it.
All right, so maybe we should get started. All right, let's think about some other challenges and problems with BGP. So this is sort of a made-up problem with BGP, but it should concern us that we can come up with these problems even in simple topologies like this. Because this could happen in more complex topologies, that is the internet. The routing table on right next to each node tells us what the routing preference is for each router when they have to send a packet to the destination that is node 0. Right? So what does node 2 prefer? What route does node 2 prefer?
Prefers to send it through one
Yeah.
rather than
Yeah. Why might that be the case? Maybe 0 always.
direct link is unreliable.
Yeah, so maybe the direct link is not very reliable, or maybe the direct link is more expensive. Maybe 0 always charges a lot of money to its direct customers. How about node 1?
We'd rather send through 3.
Yeah, would rather send it to 0 through 3 than directly, right? Okay, let's say in the beginning we have just that route, in which case, well, you just have to use that route if that's the only one that you have, right? So if 2 is using that route, so 2 is going to advertise, okay, I'm sending packets to 0 directly. And what is 3 going to do? What would 3 do when it receives that advertisement?
It's going to say, well, I can send them directly, but I'd rather send it to you.
Yeah. Does that make sense? Yeah, okay. How about, let's say 1, when it starts, let's say it starts sending directly. So this preference just means that you're going to use the route that you prefer if there are options. If, let's say, 1, 0 is the only route that you have at a given time, then you're going to use that, of course, right? Even though that's not the one that you prefer. So what is 1 going to advertise? 1 is going to advertise that I have a direct route to 0. So let's say that advertisement reaches, which nodes receive that advertisement? 2 nodes. 2 and 3. So let's think about node 3. So node 3 is going to receive this advertisement saying, I have a route to 0. So what is 3 going to do?
Well, it doesn't prefer a route.
Yeah, look at the preference table. 3 doesn't care what routes A has, because 3 basically says if there's a route 3 to 0, I'm going to use that. And if that route is not there, and if there is route 3, 0, I'm just going to use 3, 0. So 3 is going to ignore that message, right?
So you don't put it in a routing table, like if there's another path?
Yeah, because you don't.
Because
You don't.
its policy is set
yeah.
to ignore that.
Yeah. Maybe they don't like each other. All right. So 2 is also going to receive that advertisement. The advertisement is there is a route 1, 0. That's the advertisement, right? So what is 2 going to do? Right now it's sending packets 20. Now it just received an advertisement saying there's a route 10. So what should 2 do?
2 is going to switch to go through 1.
Okay, great. So 2 is going to now switch to go through 1. Now, that route goes away, right? 2 is no longer sending that route. Now, what is 2 going to advertise?
It's going to advertise 210.
So 2 is going to say, I have 210. Right? Okay. What should 3 do?
3 says, well, that's not a route I like, so what's the next route I like, which is 30.
Yeah. So when 3 receives the advertisement that 20 is no longer available, the route that's available through 2 is actually 210. 3 says, well, my preference says I highly prefer 320, but it seems like that's not going to be available anymore because 20 is gone. So what's the next route? 30. Does that make sense? Now, what is 3 going to advertise?
That it's got a direct route to 0.
So which nodes receive that advertisement?
1 and 2.
1 and 2. Let's think about 2. So 2 receives advertisement that there is 30. So what is 2 going to do?
Ignore it.
Ignore it because I actually don't prefer that route, even though there is a route, because what I prefer is 210 if that's available, and if that's not available, I'm going to use 20, right? But node 1 also receives that advertisement. Okay, there is route 30 now. And what is node 1 going to do?
It's going to switch to that.
Yeah, it's going to switch to 130 because node 1 actually prefers a route that goes to 0 through 3. And route 10 is going to be withdrawn, right? So when route 10 is going to be withdrawn and 130 is going to be advertised, what is 2 going to do?
2 is going to turn its direct route back on.
Yeah, 2 is going to turn to the route that it was using previously, which is the direct route. Because 10 is no longer available. If it was available, it would have preferred that. So what's going on? So if you look at a particular node, what's going on?
It's turning its direct route off about a third of the time.
Yeah, so there's the oscillation going on here. So this could be a little bit confusing, but fortunately we've recorded this. So you can look at it again if this is a little bit confusing. But the point here is it is possible to come up with a configuration. 2 things there, right? One is the topology, and another is policy. It is possible to come up with a topology and a policy that leads to an unstable situation. Any question about this? So the researchers were able to show that you can come up with this type of scenario even in a small topology. In a larger topology, you might not have exactly this problem, but you get the flavor for the type of problem one should be looking for. Right? Even in a larger network, maybe there are some parts of it where you might have this problem, or even if it doesn't oscillate back and forth, maybe we have transient oscillations. When links go up and down, maybe the graph is configured in a certain way that the routes might oscillate for some time. Any question? Okay. All right. We're going to talk about security a little bit now when it comes to BGP. Before we get there, I just wanted to remind you about the nodes that are running BGP. It's not all the nodes in the internet that are running BGP, right? Who is running BGP?
The nodes at the borders between it.
Yeah, so the nodes at the borders between different autonomous systems, they are the ones running this protocol. And they run it over TCP. Talked about that, right? Okay. What What does a border router announce at the highest level? What's the advertisement? What are the key pieces of information in that advertisement? It's announcing that these are the IP addresses to which you can go to through me. That's what the routers are saying, right? The routers are saying, I know how to route packets to this set of IP addresses. So this is the message that the routers are exchanging with each other. But there is a problem with this model. What if somebody else advertises that you can get to the IP addresses that you own through those other routers? What's the problem in that case? And the packets for that address is going to go to a completely different router. Right? Let's say UH downtown starts advertising to the internet all of the IP addresses that are here in this campus. What's going to happen? Let's say we have a router in Boston. So what is that router going to think?
I think that's a route to those IP addresses.
Yeah, so let's say they want to go to the course web page, our course web page. These packets are going to be directed to UH downtown, not here. You guys see the problem? So that's called prefix hijacking. Basically, another autonomous system originates the prefix that it should not have originated. Basically, it should not advertise the prefix that you don't own. That you don't own or that don't belong to your customers. Right? Because your customers are also sort of within your own network because you know how to route packets to them. Right? Okay. Here's a more concrete example. So we have one autonomous system that actually owns that IP address, but somebody else says, I know how to send packets to this IP addresses. And what's the problem here? So now some of the packets might actually go to the autonomous system that actually does not know how to send the IP addresses, and it might actually be doing that to capture the packets. Right, so the packets might actually get there. So some of the consequences are black holing. For example, all the packets are going to come to this autonomous system and it might discard that. That's going to cause huge disruption. Right? You could snoop the traffic. You might eventually send the traffic back to the original autonomous system somehow, but before the packet gets there, you save it for later analysis. You could do that, right? Because all the packets are going to come to you, and then you're going to forward to the destination. And you could do impersonation as well. So why is it hard to solve this problem? Why is it hard to solve? Is this a hard problem to solve? So first of all, everyone understands the problem now, right? This could happen in real life, right? So this voting system, it says, okay, give me your name and PeopleSoft ID and birthday. And somebody goes there and says, da, 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 here's my vote. How do you solve that problem? You might have to think about similar solution to solve this problem. It's the same thing that's happening here, right? This completely random router says, all the packets that need to go to uh.edu, just send it to me. I know how to send it there. And I have a really great path to send it there. That's what the routers are saying. So how do we solve this problem? Yeah, so we need a way to track who owns which autonomous system is allowed to advertise what routes, right? Otherwise, we're going to have this problem. Does the origin even know this is happening? Let's think about the voting case. You might eventually find out.
But how do you know in the situation if it's the right place or not? They're just saying, hey, I can do it.
Yeah.
Because they're just going to forward it along some path.
Yeah, exactly. But if you were expecting some packets, and if it didn't come there, then you can guess, okay, maybe something funny is going on.
If
I
you're
just-
expecting specific traffic,
Yes.
you've got really good historical data.
Yeah, exactly. If you know for sure that you're expecting some packet and it didn't come there, so maybe somebody else black holed it, right? In the voting case, well, I was expecting to go to this website and cast my vote, but it says, oh, wait a minute, somebody already cast the vote for me, right? It's the same kind of thing. The original autonomous system might not even know about the real route. And sometimes, even though you receive the packet, it's possible that it actually went through all these bogus autonomous systems, right? If the packet doesn't come at all, then maybe you can start guessing. But if it did, and maybe someone already snooped on these packets. So how do we diagnose prefix hijacking? First of all, we need to understand if it is happening. So how do we do that? You need to put observers at different parts of the internet and try to understand the routes to a given destination, and does that make sense or no? Right? You could also do sub-prefix hijacking. So let's say that autonomous system is the legitimate owner of that prefix. This autonomous system starts advertising this prefix. And why does sub-prefix hijacking work?
Because stuff prefers the more specific.
Yeah, so this is because of the way BGP works that we discussed earlier. If there are multiple matches for the same destination, then you prefer the most specific route. It's like saying if I'm driving from, let's say, Dallas to here, and let's have a set of directions. One set of directions says, okay, this is how you drive to Houston. Another set of directions says, okay, this is how you get to UFH, and another set of directions that says you actually, this is how you get to this particular building. I prefer the most specific one, right? Because I actually need to go to the particular building. If I had to just pick one at the origin, I would pick the most specific one. So similarly here in this case, this ISP advertised a more specific prefix. Why is this more specific? Why is this more specific?
Because its mask covers a lot more bits.
Yeah, so that slash 24 means the first 24 bits are fixed. All right. So we understand how this works now. Any question, at least at the high level? You can look at the slides for just a little bit more detail, but I think you get the idea, right, of prefix hijacking. Okay. Now we're going to watch a video. I don't know if this works, but let's try it.
The YNCC operates 14 route collectors worldwide. These collectors receive BGP updates from almost 300 peers. Let us look at what the YNCC Routing Information Service saw of the recent unauthorized route announcement affecting YouTube. This is BG Play, a tool developed by Roma Tre University in Italy in close cooperation with the YNCC. The red circle at the bottom right represents Pakistan Telecom's autonomous system number 17557, and the red circle on the bottom left, the YouTube autonomous system 36561. On February 24th, at 1847 UTC, Pakistan Telecom started to originate a /24 covering address space assigned to YouTube. We can see that this route spread rapidly in the part of the internet observed by the YNCC Routing Information Service. Within roughly a minute, the route is visible at most of the autonomous systems shown in this animation, and traffic starts to flow towards Pakistan. "17 minutes later, at 20
So what should you do if something like this happens? And we're gonna look at the rest. I think about a minute. Let's pause there and maybe think about it for a minute.
You say, what should you do?
Let's say you're
when
Google.
you're in which role?
Let's say you're Google. What would you do?
For Google?
Yeah. YouTube is owned by Google, right? So. If you're in Pakistan, what would you do? If you're this ISP in Pakistan?
Well, the question is, was that a mistake, or do you have some kind of beef with YouTube?
I think it's a mistake. Is it? So let's see what happened. Let's look at the rest of the story. Oh, does the full screen work here? Is that full screen?
Next
one
over.
over.
Next one over. Oh yeah, it's better, isn't it? So.
07, YouTube starts to announce the same route itself in order to route the traffic back to its own servers. Another 10 minutes later, around 2017 UTC, routing policy changes occur that move traffic for this route away from Pakistan Telecom's upstream PCCW AS3491. Another 20 minutes later, Pakistan Telecom's autonomous system number is repeated in those routes announced by AS3491 in order to make them less preferable. Another 8 minutes later, the unauthorized announcements are no longer propagated, and both routing and traffic revert to YouTube at around 2103 UTC. These animations and many other tools are publicly available at riz.ripe.net. There are also prototypes of new services, such as the Riz dashboard shown here. Please pay us a visit on the
Right as it ended, you can see some oscillation in some of the stuff.
Yeah. Also, did you notice the difference between, they were talking about routing information and traffic. Did you notice that? Why are they different? There are two kinds of things going on here. Exactly. So it takes a little bit of time for traffic to actually start using the routes that the nodes are starting to discover. All right. So I think we have one other quick topic in the last few minutes. All right. So this is the summary. So do you understand what the problem was? So what was the government trying to do? It was trying to black hole the traffic from,
Their citizens to YouTube.
yeah. But what is the mistake that they made?
They black holed the traffic from everyone
Yeah.
except their citizens to YouTube.
So do you see that? So if they had, if the ISP had advertised to all its customers that, okay, you know, I'm responsible for routing all the traffic to YouTube, then all the traffic would have gone there and they would have basically shut down those connections. But that's the mistake that they made. They actually sent this advertisement to the internet, so other ISPs thought that's a legitimate route to YouTube. So there are many other things that can cause havoc. So spammers can steal unused IP addresses. Because there are a lot of IP addresses that are not used. You can announce these very short prefixes. And why would you want to do that? Well, why are spammers interested in stealing unused IP addresses?
So it can't be
So it
sent
can't
back to them.
Yeah. So let's say you want to set up a web server. Let's say. I mean, there are many reasons why you might want to do that. Let's say you want to set up a web server, and you don't want to be detected. What are the kinds of things you might want to do? Because a lot of times they're tracking your IP address, right? So let's say you want to use a completely random IP address, but the rest of the internet still needs to know how to route packets to these random IP addresses. It's not sufficient that you pick a random IP address and everyone knows, what that server is. Let's say you want to serve a scamming website and a random IP address. You need to tell the rest of the internet, okay, here's the IP address. So you might actually need to advertise some of this. Here's another interesting incident. Let's talk about one more. It's related to more traffic engineering type scenarios. Sometimes you might want to remove an AS path or an autonomous system from the path you are advertising. Why might you want to do that? Because there are these policies that determine which paths you're going to select, right? So let's say the actual path is 701.371.5 and 88. You might just say, okay, here's the path to this destination through me, 701.88. Why might you want to do that? Maybe you want to attract traffic through if someone is using shortest path. Because the path looks shorter now, right? To your peers, the path is going to look shorter. Sometimes you might have policies to avoid certain ISPs. Now you're not going to let them actually use that policy. They don't even know if autonomous system 3715 is on the way. Why might you not want to send some of your traffic through a particular autonomous system?
You don't trust it.
Yeah, you might not trust them, or maybe they are known to, archive all the packets. There could be many reasons. How can you tell if this is a lie? Let's say you received an advertisement saying, okay, 701.88. That's a lie, right? The actual route goes through 3715. So you got this advertisement. It's a lie. How can you tell if it is a lie?
Trace route.
You might be able to do trace route, but even there are ways to get around it. You can modify these packets, right? Even the trace route packets. You could also add some autonomous systems. Why might you want to do that? This allows you to block some unwanted traffic by creating loops that don't exist, for example. So this is the last slide. That also provides an example for why you might want to add an autonomous system at the end of the path. And one reason you might want to do that is if you're advertising a prefix that you actually don't own, let's say you came up with this system to detect that someone is advertising a prefix that you don't own, right? Let's say I start advertising a route saying, okay, I'm Rice University, and send all the traffic here. But if you look at the autonomous system path, it'll show UH and level 3, etc. There is no Rice University in that path. But what if at the end I also put Rice University at the path? Then the other routers, they might think, well, the origin of this path, it seems like it terminates at Rice University through U of H, so it seems like this is a legitimate path. That's what's going on. Do people understand that attack?
You're tricking them into think that you have a path that you don't really have.
Yeah, exactly. And you're even putting the right autonomous system in this particular case. You're not only saying, I can route to these IP addresses. You can say, oh, I also have a link to that autonomous system, and here it is. So you're actually making it even harder to detect that. All right, so we're going to just stop this conversation here, and we'll just talk a few missing pieces about BGP next time and move on to other topics. All right, thank you.